Okay. Somehow I could repeat this lecture slide because this is very important. It highlights all the details we went through in the last lecture, and it also predicted some upcoming stories. Okay. So this is the circuit diagram of resonant converter, or we just showed the part of resonant inverter, and this is the VCO. No, VCO is not here. This is the input. Right? The input to this one, which is integrator, this can be considered part of your logic circuit or part of VCO. So input to the VCO is this one. Okay. So VST is omega ST is omega SO times some time varying component, and this omega SO defines here. Okay, it defines the unmodulated switching frequency. Okay. And switching frequency is modulated by this sinusoidal wave. This is the variation, magnitude of variation. This is frequency of modulation. Okay? So this switching frequency is changing, and the rate of the changing, speed of the changing is modulated by this omega m. And it goes into integrator. It becomes as this is phase. Okay, and this signal is cosine, sinusoidal of this one becomes this tank voltage, and tank voltage is actually this rectangular waveforms with the variable frequencies, something similar to this, but we are just considering this fundamental component of this one because this tank circuit has high Q. It only responds to the fundamental frequency component, sinusoidal component. So that is shown here, right? And so this sinusoid is actually a combination of the many sinusoid. So at this region, this frequency is slow, frequency is fast here. The pattern of this variation is sinusoidal at the frequency of omega m is totally different from the switching frequency omega s. They are related, but it's a different concept. So when frequency is slow, we are somewhere here. Okay, this is the gain curve, so gain is large. Then with this, magnitude will be large. So you have large magnification, and at this high frequency range, with this high frequency, magnitude will be small. Then you have small variation. Okay, so you can think of this. So because this frequency is varied around this area, so at the low frequencies, magnitude will be large. And at this frequency, magnitude will be small. So variation of magnitude, which one is this? Which is this? We call it envelope. So variation of this envelope follows the variation of, will follow variation of this. Okay, that is our common sense or reasoning or educated guess. So that is true. Actually, this one is variation of switching frequency here. And this is a variation of this envelope, just a connection of the peak point, very like this. And this length, magnitude of this variation is same as to variation of this, or very similar to this. Okay, that is my assumption or my presumption. I didn't check that is mathematically correct. Probably it is correct, but I didn't prove it. But this assumption helps to explain this to you. Okay, later on we will fix this one to the exact science, and I'll explain the difference between this presumption and the mathematical fact. Right? So this might be observable. Then with this, you have this variation in magnitude of envelope, maybe this much. This can be considered as output. So we just consider only AC part of this. So this is called AT, whole thing, biased here. Then we subtract the DC component here. Then you will have this AC signal. So magnitude of this, which is the magnitude of variation in envelope, is A magnitude hat, small a, is the output of this process. That input of process to this is this one, actually this one. All right. So variation of the switching frequency comes in the denominator, and the variation of magnitude here comes in the numerator. That is called transfer function. Okay. So, but this ratio of this thing, this magnitude ratio or phase in between, varies with the speed of changing this frequency. That is very strange. Okay. So, if you change this very slowly, like this magnitude will be relatively large. Or if you change it very fast, so you have this kind of variation in modulation frequency, then magnitude will be different. Okay, there is something very hard to understand, or hard to comprehend, or hard to swallow. But that is true. The mathematical treatment of this proves that. Okay, so with that, suppose you did this practice at this frequency, at this particular frequency. That means unmodulated switching frequency is somewhere here. So ratio between this unmodulated switching frequency and resonant frequency of this tank circuit is 1.2. So you are somewhere here. Okay. This axis represents the switching frequency. In relative sense, this is a ratio between unmodulated switching frequency and this is resonant frequency of a tank. That means you are doing this practice at this point, at resonant frequency. Okay. Then this variation of this slope is 0, is a horizontal part. So this gain is 0. Okay. So if you increase this, somehow you select this point, and this point is this one. So ratio between this unmodulated switching frequency and tank resonant frequency was 1.2. So you are looking this picture from here. All right. So you are looking this slope, this curve in distance. This is the same thing. We moved this curve to here. So you are watching that curve here. So variation occurring here, right? So at the given frequency of omega SO, at the fixed unmodulated switching frequency, so that is one point along this line. Okay. Suppose this variation, this modulation frequency is this one. No. This one. Okay. 1 kilohertz. This is the 1 kilohertz point. Then you have some value of this one. This one. Okay. So this line is the practice of this at the fixed number of this ratio is fixed. You are only changing this del VO, this one. Del omega S is also fixed. You are just changing the rate of speed of this modulation. Then you have different values. Okay. So now you move the unmodulated switching frequency at this point. This is below resonant frequency. So this one is easier to explain because we have this. This is the sliced view of this, cross-sectional view of this. So in this case, it's easy to explain because this omega S is varied along this line. So omega S is varied here, okay? So you are modulating this one at different frequencies. This is the modulation frequency. This is the low frequency. You have some value here, and you increase that to 1 kilohertz, omega m, then you have this value. This is a connection of this one. Okay? So you have one curve at this cut. If you move the cutting to this side, you have another slice, another slice, another slice, another slice, something like that. Okay? So this figure is very good because showing this and this is very informative. Okay? So you are looking this at distance here, and you're playing with, you are changing this frequency here. Then you evaluate magnitude of this one, divide by something, this one, and put that number here. Okay, connect. Right. So this one is maybe qualitative description of the process of what you are doing here. What you are trying to do is to find the equation of this one. Okay. it varies with this change in the unmodulated switching frequency. Okay? So this dynamics is very complicated. You have dynamics in this curve alone, and you have another dynamics along this line. So very complicated problem. All right? So this is the story about our target or our path in this section. All right? So we just forget about this, and we go back to the algebra, and we go through the algebra step by step, and finally we come up with equation of this one. Okay? Good. So next step is different from this type of discussions. This one looks complicated, but this one is easy to explain and to understand. This is just the simple mathematics, maybe high school mathematics or freshman mathematics. Okay. First one is this. This one is the frequency modulate sinusoid VT1. This is the tank voltage. I sketch tank voltage in this manner because the average value of this is unmodulated switching frequency, and this one is modulated switching frequency. Okay, the degree of modulation was maximum, minimum, and so on. Right? This is a graphical representation. We have a mathematical representation of this waveform. Right? So that was shown previously somewhere here. This one. Okay. So this is the equation of VT1. So we has cosine, and we have two time varying components. One is this one. This whole thing can be considered x, and the other one considered with y. Okay. This is some special expression because usually this cosine function has only one term involved with t, but we have two terms varying with time. Okay. So if you plot this one, then maybe it looks entirely different. This is the conceptual illustration. I don't know how this one will look like. It's something similar to this, but very, very complicated, and maybe variation is very slow, so you need this much length to explain all the dynamics, but I just showed a couple of them. Okay, so this is considered as the conceptual illumination of the whole procedure, and this number beta is called modulation index. The communication people, they love this beta. Okay, so this is very important number. So go back to this simple mathematics. All right. So this is our equation, and this is beta is called as modulation index. This is the ratio of this modulation frequency and the variation in the switching frequency. Usually this is very small, much smaller than 1. All right. So we have cosine something plus something. Maybe we call it x, and we call it this x, and we call it y. So we have this expression. This is the basic equation for this trigonometric function. In Korea, we call this Koko Sasa. Okay? Something Koko Sasa comes out of this, so we'll use this. All right? So because we have x, where is x, y, okay? Koko xy, Sasa xy. All right? And this can be simplified. If beta is very small, this reduced to 1. Okay? Cosine x, x is very small. That value is just 1. Sin x, x is small. That value is just x. Okay? That is the first order approximation of Taylor series expression of cosine and sine function. So we use that. So this comes from this Koko Sasa formula. Then you have this. So this becomes 1. You have this term, and this becomes beta. Beta is coming in front here, and we have this, right? So you have B. You have another equation, right? This is some equation. So some formula, right? So with this is, we don't have to play with this. This stands alone, and this term is split into two terms, One is this one. One frequency is omega SO plus omega M. The other one is omega SO minus omega M. So only three terms are important here because of this approximation. Right? So we need to consider only three components, which is this one. This is unmodulated sinusoid, and this is frequency is increased by this omega 1, and this one frequency is decreased by omega 1. Right? So we have this spectrum of this VT1. Okay? So this is the component of unmodulated switching frequency. This is called upper band, is band, side band, upper side band, lower side band. So we only consider three components here because of this one. Okay? This is one approach. So to approximate this one, this complicated expression, we just use this, taken from the high school mathematics. We come up with this. Okay? There is another approach. Second approach. So people usually use this. This is some strange function. Okay? So there is omega SO and omega M, and this can be expanded into infinity series, something similar to Fourier series, but the coefficient is time dependent, some strange number. So you have this one, then this is expanded. This harmonics of this omega SO plus minus, this is harmonics, right? This is the infinite series, and this coefficient is called Bessel function. Okay? I don't know the Bessel guy. I don't know what Bessel function means. I took the result from the table, mathematical tables. So this can be expanded into this infinite series. So there is one coefficient, another one. This is the fundamental component. This is the sideband of the first sideband, second one. Okay, but this coefficient of this Bessel function of order n is this one. Okay, this is J-O beta just 1, and this one is beta divided by 2, and this one is 3 factorial times this one squared, something like that. So it reduced very fastly. So we forget about this. Only take 3 components into consideration. This one, and that result is exactly same as the previous approach based on the high school mathematics. Right? So they are the same thing. Okay? Maybe you need to consider the another sideband here. Then you should use this one. Okay? But usually this one is more. We'll have more trouble than enough. You do this. Okay? You don't want to go any further. Okay? So this is the result. Right? Then this is the graphical representation of the result. This is the Planck function. So the input of this process was 3 things. One is this unmodulated switching frequency, and this is the modulation frequency, and this is the magnitude of modulation. 3 things are input variables. It goes into the switch network, and the output of a switch network is sum of this one, and this one, based on the previous approximation or the coefficient of the Bessel function. So only 3 components are considered, right? So maybe you combine these things at different frequency, only 3 sinusoid, you cannot come up with this. Okay? I don't know. But this is the conceptual representation. So I don't bother with this, right? The conceptually is okay. The difference is previously you are assuming that the switching frequency spans this length. It spans from here to there, so on. All right? But in here, just it says only 3 components are necessary. The other ones are there is something in between. They can be ignored somehow. I don't know why. Maybe that the Bessel function or some approximation we used, they can be ignored. Then result is very simple, right? So with this, this unmodulated switching frequency is split into three components. This one, this one, this one, and this three sinusoid excite this one. Then output of these things is first one is this unmodulated switching frequency sinusoid is multiplied by this. We have one output, another output, another output. We sum them together. Okay, that is the superposition of frequency response of sinusoid at different frequency, but that they are closely related with this relationship. Okay, this is the carrier frequency. It's called the sideband. This is another sideband, and each of these sinusoid is simply multiplied by this magnitude of this curve at this particular frequency, right? And this one is coefficient of this one. It comes from this DC voltage, okay? So, you know, the relationship between this voltage and this voltage, 4 divided pi, something like that. So, we have three terms. First one, second one, third one, okay? Then, this is the sinusoid. This is a sinusoid, and this is what? This is a constant, right? This is a constant. This is a constant, but this is what? This is a phasor, okay? So we have one phasor here. It has magnitude and phase. It is a phasor, complex number. We have another phasor. Okay? We need to consider three phasors now, and some of them are this time domain expression of this VRT. Okay? So replace this with AU. Maybe A means amplitude, U means upper sideband, and this one is what? This one is carrier frequency, and this one is lower sideband, something like that. Okay? So this is notation of phasor. So AU is a phasor here, and this A0 is a phasor, AL is a phasor. Okay? So we have three phasors combined. Okay? But phasors are their vectors. So we should consider this as the vector summation. So we separate the magnitude and the phase, okay, to deal with the phasor manipulation. All right. And one thing interesting is this is A0 is also phasor. So this is a phasor, all right? This is the H evaluate at this frequency. It has magnitude. The phase is not shown here, but it has phase characteristics. Right? When this one is 0, omega m is 0. That means what? No modulation. Okay? So modulation period is 0. Then this varies infinitely. Shape is flat, so it's not changing. So there's no modulation. Then you just forget about this. Then only you have this. Then you come up with this. Or maybe you consider this. They'll cancel because one is beta divided by 2. The other one is minus of that. They cancel. So anyway, you will have only this one. Later on, we use this fact, okay, to evaluate something. So this is necessary to mention here. Okay, so right. So what we are trying to find is somehow find the relationship between this del omega s and the variation of envelope magnitude. This one. Okay. So for that purpose, I did draw everything. So this is the output of tank function, tank network. So this is amplitude modulated and phase modulated. Okay. So this is a combination of amplitude modulated and phase modulated, frequency modulated sinusoid. It is combination of AM and FN signal. So which one is this? So this is envelope is expressed like this. So this envelope itself is denoted as AT, large AT. And this is the DC bias, A, O, A naught, this magnitude, right? And this is the magnitude of this sinusoidal component. So we just take this part here, or we subtract this one from AT. Then we have this. Okay, it's the same thing. Okay, conceptually, graphically, just take the AC part, or numerically, just perform this operation. So this AT is actually AT minus this magnitude of this DC bias component. Then we have this, right? We call it envelope sinusoid, magnitude of that. So somehow we want to have the relationship, describing relationship between variation of omega, del omega s, and the variation of this, magnitude of this. Okay, that is our eventual goal in magnitude and in phase, right? So we know this. We have the expression for this in the previous one, and we have this one, we have this one. Then you will go through the pages of manipulation of this phase notation. Okay. I didn't went through all the details. Erickson did that. So from his result, he showed some derivation, all the details. He is very, very patient guy. Okay. So patient guy. So he derived all the details, and nicely, lengthy phase analysis, very lengthy, extremely lengthy phase analysis proved that this AT, this one, okay, this one is the sinusoidal waveform. So it has phase and magnitude is expressed like this. This is the magnitude of this one, this sinusoid, and the frequency of this sinusoid is omega mt as we predicted. Okay, and it has some phase component. So this is the expression for this one. Okay, and it's called envelope sinusoid here. And relationship between this magnitude of this sinusoid, envelope sinusoid, and this one is shown here. Okay, he derived this. Maybe I don't know who derived this. It takes pages of some mathematical debris, some junks there. Then result is this. The result is this one is the same as this one. This is the magnitude of this. Okay, DC component of this part, and this is this one. The phase of this one. Take the complex conjugate shown here. We define this, and we define AL, and use the complex conjugate of AL star. Right? So this is the result. Okay. So this is the magnitude. If we evaluate this, then we know how it varies and what will be the magnitude of the sinusoidal variation. Right? So we won't go through all the details about that. I trust him, so I took his result. All right. So this is the magnitude variation. This is the phase variation. Right? But this phase variation is this one. This is the phase of envelope sinusoid. But you can divide this whole thing by constant. They don't change the phase at all. Right? Phase remains the same because the phase of this DC is 0. It's not changing anything. So phase, you divide inside of this phase symbol, this one. Okay? So this is necessary in the next page. And this three phasor is defined as this. This is magnitude of this, okay, VT1 is the fundamental component of tank voltage, magnitude, VT1 times beta divided by 2. Beta is defined as the ratio between del omega s and omega m, okay, plus minus. Right? So with this, we have, again, this is the repetition of previous slide. Okay, so I'm repeating some important pages. okay, again and again, because it's not easy to accept, swallow, okay? So what we are doing is this one. You have a switch and tank network, and input to the process is this one, and actually input is considered as this variation in switching frequency centered around this unmodulated switching frequency. And with that, through this tank, we have some waveforms similar to this, and there is a AC variation in its envelope, connection of the peak values here, and we take only AC component over here, okay? So transfer function from this is the input, and this magnitude of this one is output, okay? No. This is the input, not the magnitude. This one. This sinusoid is output. So we call it frequency to envelope transfer function. Okay. So if we find this, then analysis of resonant converter is done, because it characterizes the inverter path dynamics, and this low pass filter dynamics is extremely simple, because you have the connection between this rectified sinusoid and average value, something, okay, pi divided 2 or something, very simple thing. And we have our filter inductor and our filter capacitor and load resistance. This frequency, corner frequency, is way below this one. This is very high frequency dynamics, because circuit component in resonant tank is very small, and circuit component in our filter is very large, maybe 100 times, something like that. So we have a huge separation. So this only specifies the high frequency dynamics, and low frequency dynamics, we just incorporate low frequency dynamics of this out filter, okay? Just add something, then you have the transfer function of from frequency to out voltage. With that, you can control the whatever compensation you need, right? That is the basic idea. So focus on this now. Okay, it's called the frequency to envelope transfer function. So it is magnitude relationship and phase relationship, right? But this is the phasor, okay? This is phasor. All of them are phasor. So this phasor, if you transform this phasor into sinusoid, you will have this. The same thing, okay? So now we only play with this, because this one is easier to deal with. Here, this originally, the phase of this one is only, it contains this component, but phase of this phasor has this one in the denominator, but it does not change, does not touch the phase information of this, right? So we can consider this. This is the, this one is a phasor representation of transfer function, output. This one, sinusoid, envelope sinusoid, has this phasor representation. Then this transfer function is very easy, okay? At least it has very easy, simple notation, easy to remember. It is not easy to play with. It is a very complex expression, all right? So this is a phasor of this one. We all know the individual of them. And this one, we know this, okay? We can calculate this, and this is the input. And input is this del omega s is start from this epsilon. Epsilon is variation in AC component of control voltage, was multiplied with Km, ratio gain, and 2 pi to be transformed to the omega, right? So we have this, right? So this is, now we have expression of this. Okay, let me highlight this. Okay, so you know the meaning of this, right? You don't know maybe all the details about derivation of everything, but you know what we are trying to do and what this expression is telling us. And next one is just evaluate this. very tedious, but not difficult. Okay, so let me explain one by one. Sorry for the mess here. All right, but this one helps. Okay, so we have this. We have 1, 2, 3, 4. Maybe just 3. This one, maybe 4. I don't know. Okay, but we know each of them. We know the expression of each of them. So A0 is this one. This is the magnitude of fundamental component of tank voltage multiplied by this H evaluate at this frequency, which is a complex quantity. So this is a phase, and this complex conjugate, it just take minus sign in front of this. Still we are assuming this tank circuit has only reactive component, so just the complex conjugate is obtained, thus replacing this J with minus J. Okay, that simplifies a lot. Without that assumption, it's impossible to play with this. And this is AL. So AL conjugated, put minus sign here. Then you have this. But this here, you have S expression. But this S is defined to omega m, right? Not omega S. We have omega S, which specifies the switching frequency, right? In here, S is defined with respect to modulation frequency, omega m, okay? So S is J omega m. So you combine these together, and you have S, and remaining part is here. And same thing here. So you have this minus J omega m, right? So minus sign is, minus, right? Plus J omega S, and minus is still there. So you have a minus, right? So this, and okay, this is the one story. There is another story. Assume we know HS. HS is what? Tank transfer function, right? So tank transfer function is simple. The transfer function of LC circuit, LCR circuit in series or parallel loaded. This one is extremely easy. So you can derive this, right? Then this we replace S with J omega m because you are talking about the modulation frequency domain. So with this, and this beta is this. So we put everything there. Okay. So, where was it? Here, right? Here. Okay. So this one, and this is A0. Previously, we defined this. Right? In the previous lecture slide, we identified this A0. Magnitude is just the magnitude of this whole thing, A0. Okay, what is called this gain product, gain product evaluate at the resonant frequency. No. Okay, unmodulated resonant frequency. Okay, so we replace with this, and this one is. One is beta. Okay, this is A naught conjugate. Okay, so you have same thing with minus sign in front of it, and this is beta. Definition of beta divided by 2. We have this, and this is with this second term with this one. Oh no. Right. This was H, right? This is H. We are just evaluating H. We multiply this one. So beta divided by 2 is coming here, and V1 is here, and this is H evaluate. We are assuming this as H, and the thing is, this S and this S is different. I don't know, not different. Okay, assume they are the same now. So this, we use J omega here, right? No, we just use S as it is, okay? So this is just the evaluation of this one. So this part, this is denominator part. numerator part. Okay, so you have another term here. I'm sorry, that's just evaluating this. All right, just symbolically doing this. All right? So later on, you take time, and I think this is error-free. I checked several times, and many things cancels. This one cancels. This one cancels. This cancels. This cancels. Okay. So actually, this whole thing is large bracket. Inside of that is just expression of this. Okay, just the bookkeeping business, nothing else. Then you put this with the common denominator, okay, large denominator, put everything together, then you have one expression, fraction type expression, which is this, okay? So this transfer function, GNVS, okay, when HS is this, HS is used somewhere here inside of this phasor, and final result is this one. Okay, so this is considered as the DC component, and this is the denominator part, and this is the numerator part. Very complicated, but you don't have to worry about this. Okay, they canceled it, or we can ignore that. We only need to consider maybe a couple of terms here, so you don't be scared or you don't be intimidated. You don't have to worry about this. Okay, so. This one is the last equation, last expression, very dirty expression, this one. And just take a look at denominator, okay? Because the denominator determines whole of this transfer function, right? So only consider denominator first, and later consider this leading coefficient, and finally consider this one separately, okay? Then make this business easier. So first consider this one. Poles of G envelope S. So transfer function is this. Only consider this one, okay? Assume we are HS is known and expressed like this. NS divided by DS, usually NS is 1, many cases. Okay? For the simple circuit, LCR type circuit, this always is 1, okay? So you don't have to worry too much about this one because this N becomes just unity. It's not there, right? So assume and denominator of this HS is expressed like this, right? So this is the usually double pole, okay? And you have we have additional pole, okay? So this is S plane. This is S plane. We are talking about the S here, right? Then you replace S with this one, okay? So here you have this. So this S should be replaced with this one. So this is S. Actually, this S, we change the variable here. So maybe it's better to use different notation. S prime. Okay, this is S double prime. Okay, but it won't be necessary if you understand this. We use same S. So this is the original equation for the denominator, and this is the equation of denominator of GENVS. It has the same form here, but we have two terms. First term is, in first term, S is replaced with S plus J omega SO here, S minus J omega SO here, right? Okay, so consider this one. Consider this one. Okay, this one. We have another expression like this. So we just consider this one. Then this part is this, right? So originally pole was here. Originally pole was here in omega S domain. But in this domain, S plus J omega S domain, this pole is moved to here. Here. Okay. It was omega at this position. It moved to here. It increased this much because you have this relationship, right? Consider this term is 0 at particular frequency. That is the pole in this equation. So from this term, with this is the pole, okay? Pole of this term at this domain, which one is this? Originally pole was this one on the near axis. Now this pole has been moved abroad by this much. It appears here. What about these two things, two guys? They'll have the same, this horizontal transition in magnitude. So originally we have 3 poles here, but after this process, we have 6 poles. These 3 of them is shifted abroad by this much due to this expression, okay? Due to this one, these 3 poles are shifted down this much. So these 3 poles translate 6 poles in this location. That is the mathematical operation of that whole things, right? Okay, so you accept this or you understand this. That's good, right? One problem with this is there is a S here. This means there is a pole at the origin of this graph. You have a pole here. This is a big problem here, right? But this pole will be cancelled if we perform this operation to evaluate the numerator. There another S term is coming out, always coming out. Then that will be cancelled. Okay, so you don't have to worry about this. It will be cancelled eventually. So assume this is not existing here. Just consider we do this. All right. So let me take some time, okay, to explain this once more. All right. So you have many things, many mathematical junks, debris, garbage, whatever. Then final conclusion is this. If tank circuit has 3 poles, then in this envelope sinusoid, okay, transfer function that has 7 poles, 3 here, 3 here, okay? And another one here, this one will be cancelled. So you have 6 poles, right? But this pole of this frequency difference is huge, right? So there is some distance in between. So forget about this. These 2 poles are called dominant poles. Okay? Only just take 2 dominant poles here. All right? Then this one and this one. Okay? And forget about this. Then when you are considering this envelope sinusoid, you only need to consider these 2 poles, dominant poles. Okay? That is we are almost approaching the final result. Let me explain once more. All right. So this is denominator of HS, tank transfer function. Originally we had additional term, first order term here. We forget about this term because this term is translated into 2 separate poles, one here, but they are not dominant poles. We only considering the dominant poles. So just consider this part and this part. It's denoted as ds prime. So ds prime. Okay, we are only interested in this term. Okay, this is the standard second order equation. You know the location of this root of this. Okay, so with this. So this is the one root, this is another root. X coordinate of root is this one, and this imaginary coordinate of root is this one, plus j, minus j. They are symmetric with respect to their complex conjugate. Okay, so you know this one. And if you draw the semicircle with this, their length is omega naught. Omega naught is this one. Okay, this frequency simply indicates the length between at this pole and this origin of this domain, okay? And the length is determined by square root of this real square root of square of this, right? And this one is the semicircle start here is j omega naught minus j omega naught, okay? So this is just the coordinate of this root of standard coordinate equation. Okay. So you know this. Okay. This is not very easy. Okay. Just evaluating this equation and find the coordinate. Okay. So control book, they love this one. Okay, this standard one. Right? And the relationship between this one is a theta is this, and you know this. But we don't need this. Right? So this is the location of this pole in HS, which generate dominant pole. Okay? There are only two poles, so they are dominant pole, but they generate, we are not considering this now, okay? They generate 4 poles, and 2 of them becomes dominant pole here, right? So we have 2 poles here, then 2 poles will appear here, okay? The relationship is just you have this, and raise this y-axis, imaginary axis by this much, and lower imaginary axis by this much. Then it is the center of frequency, and you have one pole here, another pole here. Same situation in the lower part of this figure, okay? So you just take 2 of them as the dominant pole, okay? So you only consider 2 dominant poles in the denominator of G, E, and V, S. Okay? Then this one will predict that the dynamics of G, E, and this AT business. Okay? So this one will predict the frequency of AT, the envelope, sinusoid. If this one will go some oscillation like this, they'll predict the oscillation of this. Okay? This determines if this is the high Q, one step change occurs, this oscillation will be large. If it is low Q, the oscillation opposite way. Like original direction was okay. Okay? Something like that. It determines dynamics of the envelope sinusoid. Okay. Let me quickly go through the up to end of this story, okay? And maybe I repeat the last part of this lecture slide next week, okay? After midterm test, okay? So okay, maybe 10 minutes, something like that. Okay. So we know the location of this, right? We know this dominant pole, 2 dominant poles, right? Then somehow we want to construct the coordinate equation which generate these 2 poles as their poles. Can you understand this? Right? So we construct this from this. Right? From this equation, we generate this plot. So we have this location. Location has been changed with this modified locations of 2 dominant poles. You want to construct the coordinate equation that has the 2 roots here, one here, another one here. That is very easy. Okay, I wrote down here. So construction of a coordinate equation that has the poles at this S1, E and V, S2, E and V. Okay, so the matter here is just consider a coordinate equation. So you have Q, omega, okay, and just to indicate we are interested in the envelope sinusoid. I need 2 here. Okay, so that was missing. Right? So then if we find out this Q, E, and B, and omega E and B, then we have equation for this one. We have equation for the denominator of transfer function. Denominator is most important. It determines the stability of the transfer function. It determines the transient response of something. So denominator is very important. So we are in the stage of identifying denominator of this envelope sinusoid. So we are trying to find the relationship between this omega E and B, Q E and B, and omega and Q of the original HS. Okay. So in here, shown is I copied this one. I copied this part, this purple color, this one, okay? I copied this to here, right? Okay, so we know this coordinate of this, right? This remains the same because x-axis remains the same. Okay, shifting just occurred this vertically in this direction and this direction. This one remains the same, right? And this is the coordinate of this is this one, but length from this point to origin is what? This omega E and B. Okay, you want to find out the expression for the omega E and B. Okay, that's all, right? Then square root of this. Okay, it has this negative real part and imaginary part. Okay, this length of this is this one because we know the coordinate of this and the coordinate of this, and we evaluate this. Okay, then if this Q naught, okay, this is the resonant tank circuit. Q of resonant tank circuit is gonna be high, very high. Okay, so Q naught is much larger than 0.5. Then this one can be ignored, and this is ignored. No, this one is ignored. Which one is ignored? Okay, okay, this Q square is okay, much larger than 0.5. So this one can be ignored. That is coming out from this square root. Then they cancel. So this term reduced to omega naught. Okay, so this is 0. Then this omega E and B is simply omega SO minus omega naught squared here, and it has a square root above that. So they cancel. So you have this simple expression. Okay? This frequency of omega E and B is difference between this unmodulated switching frequency and the resonant frequency. Okay, result is extremely simple. Okay, and Q is this one. Q is this one. Okay, then this x part, this x coordinate remain the same. This is original expression. This is the new expression. They remain the same. Okay, just omega naught is replaced with omega E and B, and this one is replaced with Q E and B. Then it simplifies. It becomes like this, and this is the expression. Maybe some case it can be further simplified, but this is the simple enough, right? So we have expression for this omega E and B and this Q E and B. Then we know everything about this quadratic terms. That term determines the dynamics of envelope. Okay. Right, example. Okay, another example. Right. So suppose we have a simple LC type, simple resonant tank circuit. Then this transfer function of tank circuit is something like this. All right. This is the transfer function of parallel loaded series resonant tank. Okay, the tank circuit we are playing with in previous lecture is exactly this form. Okay. Then maybe we need to go through something the process, but result will be this one. Denominator is we have same this quadratic function, right? But we have same structure here. Only this value Q and omega will be changed, right? So this is a second order system. So we have this pole here. Actually, this was a first order system, but we ignored the two poles. Non-dominant poles are ignored, so we are only taking the dominant poles. Then we have this, okay, and this one is, so we used G and BS, but this takes in the denominator only the dominant poles. Okay, we have additional quadratic term here, but we ignore that. Okay, assume there is some gain here. Okay, after this translation, by changing the playing with the numerator, assume there is some constant here, and this omega g is additionally created from the numerator business. Okay, this is assumption. Maybe you can ignore this. Still, you can assume everything is 1. So you have km, or you may have additional 0 from the denominator. Here we don't have 0 at all, but we have the term, denominator, this complex term involved with the 4 items will generate 1, 0. Okay? So we know this. From here, we know this omega naught, this is resonant frequency of tank circuit, and we know the switching frequency, unmodulated switching frequency. Okay, that is the carrier frequency. You select the steady state switching frequency to place the vision for the GBS or something, or a good line node efficiency, whatever. Okay, so this is known. Right? This is known. Then this frequency is also known. This is omega S naught is what? This is unmodulated switching frequency. You select this frequency, and this is what? Filter. Resonant, I don't know. Tank resonant frequency, and difference between them is this frequency. This frequency. Okay? Omega E and B is different from this one. Okay? And the Q factor will be different. So original Q factor was this one, but new Q factor as you have this term. All right. So peaking, it starts from 0 dB. So peak value is this one, but in here this one has this leading coefficient Km. So it starts from this 20 Km, and this value is just distance between this and this. Okay? So this is misplaced. So actually, what I mean was length between this peak point and this is this one. Okay? So this one is omega g. Okay? Don't pay attention to this. All right? So this will determine what? Major dynamics of this one. Okay? All right, let me explain one thing. Suppose you built series resonant converter and you start up your converter. Okay? Then tank frequency, that is fixed. Switching frequency is fixed. Okay? So tank frequency will be increased. No, tank current. Okay, something like this. Right? This is the unmodulated case. Okay, but you modulate. Okay, not that one, not that one. It's not that one. But in reality, it looks like this. This transient response, startup response is something like this. Okay, so where this dynamics is coming from? This low frequency dynamics is coming from. That is coming from this pole. This pole is generated. Okay? The pole frequency is the same as the frequency of this one. It's called the beat frequency. Beat, heartbeat. Heartbeat. Your heart is beating always, otherwise you are dead. Okay? So this is a heartbeat frequency. It's called the beat frequency. It's simply difference between this switching frequency and tank resonant frequency. Okay? So that is coming from this dynamics. If Q is very high, then this beat frequency dynamics will be something similar to this. Okay? If some transient response is occurred in the node or somewhere, then transient response I don't know how to draw. Something like this. And this frequency is coming from that frequency. Difference between switching frequency and resonant frequency is called the beat frequency. Okay? You may call it beat frequency. It's the same as E and B frequency. Same thing. Okay? Okay, we stop here. And after 2 weeks, I'll repeat this. Okay. So maybe it's not easy to understand everything for the first time, but I'll repeat this several times. So I'm repeating, and some critical idea, okay, to embed that idea into your brain. All right. So you don't have to worry about much now. Later on, you will know this. Okay. All right. Thank you.